Welcome to our next lecture in Chapter 4 for Elementary Statistics at Dallas College. This is Chapter 4, Section 3, Conditional Probability and the Multiplication Rule. We are going to compute conditional probabilities, compute probabilities by using the general multiplication rule, compute probabilities by using the multiplication rule for independent events, and compute the probability that an event occurs at least once. Let's first look at conditional probability using an example. Approximately 15% of adult men in the U.S. are more than 6 feet tall. Therefore, if a man is selected at random, the probability that he is more than 6 feet tall is 0.15. Now assume that you learn that the selected man is a professional basketball player. With this extra information, the probability that the man is more than 6 feet tall becomes much greater than 0.15. A probability that is computed with the knowledge of additional information is called a conditional probability. The conditional probability of an event B given an event A is denoted by P parentheses B vertical slash A and then close parentheses. The probability of B given A is the probability that B occurs under the assumption that A has already occurred or is occurring as well. And the way we compute this probability is it's the quotient of the probability of A and B, so that your event includes both, divided by the probability of A. So in this case, we would say the probability that the man is taller than 6 foot and a basketball player, right? And divided by the probability of being a basketball player. So let's look at an example. The following table presents the number of U.S. men and women in millions, 25 years and older, who have attained various levels of education. I've included both of the formulas for conditional probability and general probability, so you have these handy. You've got a table of data here that lists men and women by their highest level of education. So the first one is, what is the probability that the random selected person is a man? What is the probability that the person is a man with a bachelor's degree? And finally, what is the probability that the randomly selected person has a bachelor's degree given that he is a man? Okay, so why don't you hit pause and see if you can figure out how to do these. They're all ratios to figure out the probability. If we're looking for the probability that the random selected person is a man, then what we're looking to do is figure out how many men there are total, which is 94,000, divided by our total population. We're just looking for the probability that we select a man out of all of these people that are here. So we have the ratio of 94 divided by 195. And so our probability is 0.4821. And that kind of makes sense. We can see that the number of men and the number of women, it's not quite equally split. It's almost equally split with fewer men. So we would expect that to be less than 50%. Okay. Again, hopefully you're doing these on your own. If not, hit pause and try them, think through them, and think what you need to do. You're going to have a more effective learning by trying these before you just watch me. And if you're anything like me, a lot of times when I watch someone else do something, like inside my brain it's saying, that isn't that hard. Like even I'm watching Wimbledon or something, and I'm watching them, hit a serve or a backhand, and it looks like that doesn't look so hard. But once you get out there and try to do it on your own, you realize there's a lot more things going on than what you just see. So again, I highly encourage you to try these problems on your own by hitting pause and trying to figure them out before I talk through them. All right. So what is the probability that the person is a man with a bachelor's degree? Okay. So here we have a combination, man and bachelor's degree. So we're going to look for men and bachelor's degree, right? That's right here. That's 17.5 are both men with bachelor's degrees, okay? And then what are we going to divide that by? We're going to divide it by the total in the population, okay? So here we have 17.5 million divided by the total population. There are 17.5 million men with bachelor's degree out of that 195 million. So that is our probability that a randomly drawn or selected person is a man with a bachelor's degree. Okay. The last one, again, hopefully hit pause. What is the probability that the randomly selected person has a bachelor's degree given that he is a man? Okay. Now this is that conditional probability. So here we have a bachelor's degree given that he is a man. So it's a bachelor's degree is the B, and given that he is a man is an A. So we're looking for the probability of A and B, a man and a bachelor's degree, which we just figured out here, a man with a bachelor's degree, man and bachelor's degree, over, given that he is a man, the probability he's a man, which is here. So we actually figured out the two parts, the probability of A, which is the probability of man, and the probability of A and B, which is the probability of men and a bachelor's degree. Okay. So this is, again, the probability of a bachelor's degree given that he is a man. So this is the probability of a man with a bachelor's degree over the probability of a man. Both of those we just figured out. Notice what happens here is the total population cancels out. When you divide a fraction by a fraction, you multiply by the reciprocal. So really this is the same ratio as 17.5, the bachelor's degree, over the total number of men, which is quite interesting. All right. So let's try another one here. Hopefully if you didn't pause before, you will pause now because you've seen how this is done. What is the probability that a person is a woman given that the person is a high school graduate? Okay, so we're looking for, in the numerator, a woman and high school graduate, and the denominator is a high school graduate, the total number of high school graduates. Okay. So the probability that the person is a woman and a high school graduate, this is a woman and a high school graduate, is right here, 31.9 over the total 195. The probability that the person is a high school graduate, we would add both of these numbers here, high school graduate, this column, divide by 195. And so the probability of a woman given a high school graduate is the probability of both woman and high school graduate divided by the probability the person is a high school graduate. And so we get 0.164 over 0.315, and we can see the probability is approximately 52%. Now I want you to think about this in a different way. When you look at this, you can see that the high school graduates are almost equally divided between men and women, with the women being slightly higher. So when we talk about the probability of a woman, the probability that the person is a woman given the person is a high school graduate, we can see that this is roughly split at 50-50 between men and women. And so we'd expect it to be right around that 50%, with it being a little bit higher because there's more women. So I think this is a real logical answer that we could almost intuit. The probability that the person is a woman given a high school graduate. Again, when you look at this, now this is a very limited piece of data. In most statistical studies, you don't have such a limited number of data fields. You usually have a lot. So it's not as easy to intuit some of this out. But given that someone is a high school graduate, what's the likelihood that we pull a woman? Again, since they're about almost equal, we'd expect it to be close to 50% and slightly higher because there are more women than men. So the formula for computing conditional probabilities provides a way to compute probabilities for events of the form A and B, or the things that are in both categories, the intersection of event A and event B. Okay, this is just basic algebra. We have a formula here. If we want to figure out what the probability of A and B is, we multiply both sides by this denominator, the probability of A, and we get another kind of equation. So we can calculate the probability of A and B if we know a conditional probability and a probability of one of the factors. And you can see here it's the probability of A and B is equals the probability of A times the probability of B given A, or the probability of B times the probability of A given B. Both of these will use A and B in the numerator, but the denominators will be a little bit different, as you can see here. Okay, this is just algebra, and it's just a way to find them if you already know a probability. So here's a really simple problem. Among those who apply for a job, the probability of being granted an interview is 0.01. Among those interviewed, the probability of being offered a job is 0.25. So after someone's applied for a job, 1 in 10 are actually interviewed. Of those interviewed, looks like 1 in 4 actually gets a job. Okay, so we're trying to find the probability that an applicant is offered a job. So we're looking for an event that is both of these. Someone gets an interview and they get a job. Okay, well, notice this is the probability of getting an interview and getting a job. So this is the probability of getting an interview times the probability of getting the job, given that they got an interview. Well, being offered a job involves two events. First, you must be interviewed, and then given that you've been interviewed, you must be offered a job. So the probability of being interviewed times the probability of being offered a job given that you're interviewed, which is, I guess, what we have here if A is interview and B is offered a job. Okay. So how come we use 0.25 instead of offered a job assuming you've been interviewed? Well, it's because these are inherent in the process. The probability of being offered a job is 0.25. And again, notice that that statistic is actually is a conditional statistic. So that's why we can just plug these two in. This is a simple plug and play because this, among those who've been interviewed, the probability of being offered a job is 0.25. So notice we could say that in a conditional language, the probability of being offered a job given you were granted an interview. In a certain city, 70% of high school students graduate. Of those who graduate, 40% attend college. Find the probability that a randomly selected high school student will attend college. Again, hit pause and see if you can figure this out. The probability of attending college equals the probability that you graduate high school times the probability that you attend college given that you graduate high school. And again, this is again that you graduated high school and attended college. So the probability that someone has graduated high school is 0.7, and the probability of someone attending college, assuming they've graduated high school, is this 0.4, 40%. The probability someone's attending college, given that they've graduated from high school, is 40%. So again, it's a really straightforward product here. And so we get this probability, this condition, this combinational or union of events, high school graduate and attending college, is 0.28. Let's look at a different concept now called independence. Two events are independent if the occurrence of one does not affect the probability that the other event occurs. Very simple, very logical, etc. And really we look at if they affect each other. If they don't affect each other, then if they don't affect each other, they're independent. If there is any kind of linkage between them, then they are not independent and therefore dependent. So let's look at two examples and we can really use some intuition here. A college student is chosen at random. The events are being a freshman and being less than 20 years old. Okay. Do you think it is more likely, or that there's some relationship here that changes the probability? For example, do you think someone less than 20-year-old is more likely to be a freshman than perhaps someone at a different age? Okay. You might think of this again like we looked at the men and then men in the NBA, the height of men. So, like in that one, we said the height of a man is over 6 feet, and the other event is that the man is in the NBA or the National Basketball Association. Well, yeah, those are not independent because if you're in you have a higher likelihood of being over 6 feet if you're in the NBA. So that is a direct implicate, and that's kind of what's happening here. It's more likely that a freshman is less than 20 years old than someone else. And so these are not independent, they are actually dependent because it is a higher likelihood that the largest number or percentage of freshmen are in fact under 20. A college student is chosen at random and the events are born on a Sunday and taking a statistics class. Do you think the day that you were born impacts or has a greater likelihood for taking a statistics class? These are just random events. They're not connected. And therefore we say that these are independent. The day of the week that you were born, it would be a weird coincidence if there was like people born on Wednesday were more likely to take a statistics test, and I just think that's unlikely. When two events are independent, then the probability of B given A is simply the probability of B. Now let's think about that. If they're independent, then they don't have any effect on each other. And so the conditional probability really just doesn't work because there is no relationship between B and A. And so again, if A and B are independent, then there is really no conditional probability formula. It's just the probability of B. Because knowing that A does not occur, the probability that B occurs. Okay, this leads to a simplified version of the multiplication rule. So if we have two independent events, A and B, then the probability that something is both A and B is simply the product of both of their probabilities. So let's try one of these. According to recent figures from the U.S. Census Bureau, the percentage of people under the age of 18 was 23.5% in New York City, 25.8% in Chicago, and 26% in Los Angeles. If one person is selected from each city, what is the probability that all of them are under 18? And is this an unusual event? So again, hit pause and then try to do this. These three events are independent. The fact that someone is under 18 in New York has no direct relationship to the age of people in Chicago and LA. So what we can do is just calculate the probability that they're under 18 in Chicago times the probability they're under 18 in New York City times the probability they're under 18 in LA. And so this is just a product of those three probabilities, which we were given in percentages. And so we see we have less than a 2% chance, 1.58% chance that all three would be individuals selected would be under 18. Now it asked us if this was an unusual event, and do you remember what the cutoff was? We call something an unusual event if the percentage or the probability, the percentage is less than 5% or the probability is less than 0.05. Okay, so this is an unusual event. The fact that we would randomly pick three people and that all three would be under 18 is a very low percentage. When we sample two items from a population, we can proceed in either one of two ways. We can replace the first item drawn before sampling the second. This is known as sampling with replacement. So we'll look at some examples in a minute. I'm sorry, I normally give examples, but for some reason I'm just drawing a blank right now, thinking of people. The other option is to leave the first item out when sampling the second. This is known as sampling without replacement. So in the first case, sampling with replacement means you take something out. Let's say you have a group of something, you take something out, record some data, and then you put it back and randomly select again. So you're not changing your population size. When you sample without replacement, you take one out of the population, right? You record some data, and then you put it aside, and now your population is one smaller, so you pull another one out, and that there's slightly a different change in probability because if you don't replace that original population item, then the population is getting smaller. When sampling with replacement, each draw is made from the entire population, so the probability of drawing a particular item on the draw does not depend on the first draw. Again, if you're putting it back, the population hasn't changed, so the draws are independent. When sampling without replacement, this means you keep the person out. The draws are not independent because you're not putting that number back into the population, so the population is changing, which changes the probability, right? Because that's our sample space on the bottom of our probability calculation. However, when a sample is very small compared to the population, again, we're using 5%, a rule of thumb is that the terms can be treated as independent. So let's say we have a population of 1,000 people and we want to select 20 for an interview. Well, 20 out of 1,000 is only 2%. So this is so small that yes, even though we do it without replacement, it's still such a small percentage of the overall population that one removal each time is not going to have a grand effect on our probability calculation. And so that's why that works. Okay. Again, here, hit pause and see if you can figure these out, if they can be treated as independent. Pollster plans to sample 1,500 voters from a city in which there are 1 million voters. We do the division. This is less than 2%. Actually, it's less than 1%. It's 0.0015. That's 0.001%. So this is definitely less than 5%. So we can consider them independent because it's such a small sample. 500 students attend a college basketball game. 50 of them are chosen at random to receive a free t-shirt. 50 out of 500, is that 10%? That's 10%, so it's not such a small that we would consider it independent. And then 50 of them are chosen at random to receive a free t-shirt. Well, when you give out a free t-shirt, you're going to take that person's name like out of the drawing, so like maybe there's a ticket or something. So this is without replacement, and without replacement is dependent. And again, first I check the numbers, 50 divided by 500, and that is greater than 5%. So we cannot just use the small size of the sample because it isn't small. So one of the things about statistics is an exact science. So you have to be careful when you say when problems or events are listed as less than, greater than, less than or equal to, greater than or equal to, or at least one, or more than three, whatever. Okay. So sometimes this is a very often case. We want to solve at least once problems. Okay, so we're looking to find the probability that an event occurs at least once in several independent trials. But again, since statistics is an exact science, you have to figure out what at least once means, okay? So if we're doing 4 samples, that means in those 4 samples, we could have 1 um, that meets our event, we could have 2 that meets our event, 3 that meets our event, or 4 that meets our event. And so that's the probability of picking 1 match of the event, picking 2 that match the event, or the probability of 3, or the probability of 4. There's 4 different situations there, okay? So at least once is exactly 1 or more. So again, if we had 4 items, this is 1 or 2 or 3 or 4. It's generally easier to calculate the opposite of the event. We can calculate such probabilities by finding the probability of the complement. This is what the event is not. For example, if we're rolling a die and the event is even, that we roll an even roll, the complement is the opposite of that, everything that's not, and this would be that we would roll an odd number instead of an even number. So if we're looking at exactly 1 or more, notice the probability is either you would say none of those or all of the any other answer. For example, if we were flipping a coin 5 times and we wanted to know the probability of getting at least 1 head, this would mean that we would get exactly 0 tails. Okay, or that would be because probability of getting at least 1, excuse me, not exactly 1, at least 1 is 1, 2, 3, or 4. The complement of that is getting 0 heads, and that means all of them would be tails. Okay? Probability of at least once. So the probability of at least once equals 1 minus the complement. The probability of the complement is that they're all opposite. So the probability of getting at least 1 heads is 1 minus the probability that you get all tails. Okay. So try this one. I pretty much kind of told you how to do this. A fair coin is tossed 5 times. What is the probability that it comes up heads at least once? Okay. So see if you can figure this out. It's pretty straightforward. And hit pause and try it and then come back. All right. Is each toss dependent or independent? Well, you might remember the law of averages, which is not really a law. It says if I flip a coin 4 times in a row, I think that the next coin is much more likely, it has a higher probability to be tails on the next one. That's not true. So each time I flip the coin, it's independent because there's 2 sides on the coin. Okay, so this is an independent event. Since the toss is not affected by the outcomes of other tosses, this is sampling with replacement. The complement of coming up with heads at least once is coming up with all 5 tails. Okay, so the probability of the first coin being a tails is 1 out of 2. The probability of the second flip being tails is 1 out of 2. And all 5 have that same probability. Okay. Again, remember this is 1 minus the probability comes up tails 5 times. So this is the probability of the first, the second, third, fourth, and fifth experiment. Remember that when they're independent, we just multiply the probability of each experiment. And again, since they're all the same, we have 1 minus 1/2 to the 5th power, or approximately 31 over 32, which is 0.96875. So again, the probability of flipping a coin 5 times and getting all heads I'm sorry, at least one head is very high, 0.96. This is close to 1. 0.97, really, 97% of the time, at least one of those coins. You can see it's very small percentage that we would flip a coin 5 times and actually get all the same, and that would be 0.03 something, so 3% of the time. All right. Let's try another one. Items are inspected for flaws by 3 inspectors. If a flaw is present, each inspector will detect it with the probability of 0.8. The inspectors work independently. If an item has a flaw, what is the probability at least one inspector detects it? Okay. So again, here we're thinking in terms of at least one, so we want to figure out what is opposite. So if at least one inspector detects it, and there are 3 inspectors, that means that 1 detects it, 2 it detected, or 3 detected. The opposite of that is that none of them detect it. So all 3 fail to detect it. If the probability that each of them will detect it is 0.8, what is the probability that each of them will not detect it? Okay. So we're given that the probability that an inspector detects a flaw is 0.8. Remember, the complement of that is that they fail to detect it, and these have to add up to 1, so that's 0.2. Again, we have the same formula at the bottom, 1 minus the probability of all opposite. So this is 3 detectors failing to detect it. They're all the same because they're all independent. And so again, we're going to have 1 minus 0.2 times 0.2 times 0.2. We get 0.992. Again, these inspectors are experienced. They have a high probability of detecting flaws. And for it to go through 3 people and not get detected, it is a very unlikely event. An office has 3 smoke detectors. In case of fire, each detector has a probability of 0.9 of detecting it. What is the probability that at least one detector detects it? Again, probably beating a dead horse here, but if the probability of detecting it is 0.9, the probability of not detecting it is 0.1, and we have, in the same case, we have 3 smoke detectors, so it's very similar to the 3 inspectors. So we're going to go through this. The complement again is that no detector detects the fire, and we've got the 0.1. Sorry. You can hit back there. I went through it really quick, but you can pause it, and you can see that it's 1 minus the 0.1 cubed. Again, here's the things that we needed to learn. Hopefully you've got that. If not, you can go back and review.